Hello, I'm Youngbum Kim from Dongguk University DTM Lab. Today, I'm going to review a paper titled Deep Learning for Patent Landscaping using Transformer and Graph Embedding. This is the bibliographic information of the paper. The paper is published in the Journal Technological Forecasting and Social Change in February 2022. In terms of keywords, the study focuses on patent landscaping, deep learning, transformer models, graph embedding, and patent classification. This study makes several important contributions. First, it proposes a novel patent landscaping model that combines transformer-based text embeddings with graph-based code embeddings. Next, the model was tested on 4 benchmark datasets and outperformed existing models include BERT. Here is the contents of the review. First, I'll explain the research background. Patents play a crucial role in R&D projects. They reflect current technology trends and help protect the legal rights of assignees. Most R&D efforts involve patent landscaping, which means collecting and analyzing patent documents. The first step in this process is patent classification, where documents related to the target technology are extracted from patent databases. However, this classification process is often human-centric, tedious, and expensive, making it a significant challenge. So the goal of the study is to identify the most relevant features in patent documents, such as abstracts and classification codes, to improve patent classification. It also aims to explore how to best represent these features using deep learning techniques, particularly transformers and graph embeddings for better performance in automated patent landscaping. Here is what earlier studies have focused on. Traditional machine learning methods like SVM and KNN have used TF-IDF features from patent text such as titles, abstracts, and claims. More recent deep learning approaches use text and citation graphs, applying techniques like word embeddings, RNNs, and transformers for processing patent data. In addition, graph neural networks are also used to embedded citation or classification code networks like IPC or CPC. Traditional classification using CPC or IPC codes lacks the granularity needed for specific R&D tasks. Manual filtering of patent documents is time-consuming and repetitive. Some machine learning models such as APL and text-based classifiers like LSTM and CNN have been explored. However, these models often struggle to generalize to narrow, project-specific domains due to limited benchmark datasets and overly broad category labels. This section of the paper focuses on how the benchmark datasets were created. The authors built benchmark datasets for patent landscaping using the KISTA patent grant reports. Each report includes expert-crafted search queries and a target list of patents. To ensure reproducibility, they developed a Python model that converts Weave's search queries into a Google BigQuery compatible format. They then used public patent data from BigQuery to collect datasets across following 4 technical domains. Since the retrieved datasets were highly imbalanced, the authors applied CPC-based undersampling to remove irrelevant patents. Unlike previous API-based approaches, this method focuses on reducing noise rather than expanding the dataset. As a result, the final datasets maintain real-world imbalance patterns while offering flexible balance ratios for research use. In this study, the authors designed a deep learning model for patent landscaping. The model has 2 main parts. The first is a transformer-based text encoder that reads the abstract of each patent. The second is the deep-to-back-based embedding models that handles metadata like IPC, CPC, and USPC classification codes. The abstract is a short summary of the patent. It usually explains the key idea of the invention. The transformer model helps understand the meaning of the abstract by learning how the words relate to each other. This creates a meaningful text embedding that represents the patent's content. Next, the model uses the classification codes as metadata features. These codes show what type of technology the patent belongs to. The authors used a method called deep-to-back to turn these codes into vectors. Deep-to-back looks at the relationship between the codes and creates embeddings that keep this structure. This helps the model understand the technical area of the patent. After creating the text and metadata embeddings, the model combines them into one vector. This vector goes into a multi-layer perceptron, which is a simple neural network. The network decides if the patent is related to the target topic or not. The input features come from two sources. The text features come from the abstract and the metadata features come from the classification codes. Other metadata like inventors or assignees were not used. The author says this because names can be written in different ways, which causes confusion. Also, these are too many unique names, which makes the model harder to train. By focusing only on abstracts and classification codes, the model is both simple and effective. It combines the meaning of the text with the structure of the metadata to improve patent classification. For metadata embedding, the model handles patent classification codes such as IPC, CPC, and USPC by treating them as nodes in a graph. This graph is built based on how often these codes appear together in the same patents. To turn this structure into unstable input for the model, the authors apply deep-to-back graph-based embedding methods. It captures the relationships between codes and converts them into vector form. Notably, CPC codes, which are more detailed than IPC or USPC, are embedded in a higher dimensional space to better reflect their fine granularity. On the text side, the model processes patent abstracts which summarize each invention. These abstracts are first converted into word embeddings used word2vec, then passes through a 6-layer transformer encoder with 8 heads self-attention and a hidden size of 512. A spatial CLS token is added to the input and used to extract a fixed length vector representing the whole abstract. After both types of embeddings are generated, one from metadata and one from text, they are concatenated into a single vector. This combined vector is passed through a multi-layer perceptron, which makes the final classification. The model is trained using a binary cross entropy loss function, which determines whether a patent should be classified as a target patent or not. Here is how they tested and validated the model. The model was tested on 4 datasets based on Kista patent trend reports, each containing up to 1 million patents. To reduce noise and computational costs, the authors applied heuristic filtering using high-frequency CPC codes. In hyperparameter settings, 2 transfer configurations were tested, one with 6 encoder layers and 8 heads, and another with 12 layers and 4 heads. The model was trained for 20 epochs with a batch size of 64 using the Atom optimizer. Input sequences were padded to a length of 128 and each word was embedded into a 512-dimensional vector. Performance was measured using average precision and F1 score, which are well suited for imbalanced binary classification. The proposed model was compared against several baselines: a transformer-based model, a deep-to-back basis classifier, an API model, and patent BERT. This section is about overall results. The results show that the proposed model performs consistently better overall compared to the baselines. In most evaluation metrics, except for precision, it achieves competitive or superior scores. For example, even compared to patent BERT, the model shows balanced performance in terms of weapon score and average precision. The model also performs particularly when embedding the values of technical costs. Combining text features with technical costs leads to better results since these features complement each other. To better understand the model's effectiveness, the paper analyzed the impact of different input features. In terms of the effects of technology called metadata, CPC, which is the most fine-grained classification, showed the best performance overall. Interestingly, for the GOCS dataset, USPC slightly outperformed CPC. To ensure a fair comparison across embeddings, all graph-based metadata features were passed through a dense layer with fixed size 128. In effect of text data, the proposed model performed well across all datasets, but the MRRG dataset showed especially good results. The authors suggest that deeper transformer structures for text help improve performance more than relying on code features alone. Among the various text embedding methods, Doc2Vec achieved the best performance compared to alternatives like Word2Vec or best text. From the experiment, several insights became clear. Combining text and metadata leads to better patent classification than using either one alone. Among the classification codes, CPC is especially useful due to its fine granularity. However, the best performing code type can differ depending on the dataset. For example, in the GOCS dataset, USPC yielded better results because it had higher representation among target patents. In cases where the dataset is highly imbalanced, using deeper transformer layers can help compensate for weak code-based signals. Finally, patent BERT achieved the highest precision, particularly when only test features were used. The paper also outlines how this approach could be integrated into a practical patent landscaping workflow. Experts define a list of keywords to search patent databases. Target patents are manually labeled from the retrieved results. A classification model is trained using the full dataset and labeled targets. Periodic searches are conducted using the predefined keywords. The trained model then classifies new patents into target or not non-target categories. Finally, engineers analyze the predicted target patents to gain insights for R&D planning. Here is a summary of the paper's main contributions, future directions, and limitations. For contributions, the authors developed and tested a deep learning model that performed well in patent landscaping tests. They also provided empirical insights into how technical costs and text features affect model performance. Finally, the study demonstrated the practical applicability of deep learning to real-world patent analysis problems. For future directions, one promising direction is to extend the model to downstream tasks such as claim generation and technology trend analysis. The authors also suggest applying domain-specific training and multi-task learning to improve generalization. Another area to explore is the use of graph embeddings to represent complex relationships among classification codes. And lastly, incorporating image data could help improve classification accuracy in future work. For limitations, the experiments were limited to just 4 datasets, which may affect generalizability. The model also didn't handle longer tasks like patent claims, though future work could explore that using models such as long-former. Lastly, the current model struggles to generalize across different technical domains, indicating a need for more flexible architectures. Thank you for listening my review.